would like to introduce Dirk Helbing, who is a professor of computational social science at ETH Zurich. He studied physics and mathematics, and after having completed his doctoral thesis on modeling social processes by means of game theoretical approaches, stochastic methods, and complex system theory, he completed further studies of traffic dynamics and optimization. Hope everyone understands what these terms mean. After he became a full professor and took on management roles within academia, as well as led research teams on topics like data science, computational social science, as well as global systems science. The work of Professor Helbing is documented by hundreds of media reports and publications. Among them, more than 10 papers were published in the journals of Nature, Science, and U.S. National Academic Journals. He has also been awarded various prizes, honorary degrees, and holds positions on various academic boards. We're very fortunate to have him with us today, so please join me in welcoming Professor Helbing to the stage.
Hello, good afternoon. Are you ready for this after lunch? Now, I was asked actually to talk about digital technology, not just AI, and the culture of collaboration, and also about opportunities and risk. And here's an advance warning. At no place am I talking about how to manage a company, right? However, the hope is that there would be some thought-provoking things I say, and that would inspire the discussion later on. Now, we are certainly living in a time of big data. So much data you cannot really imagine, and this has actually inspired some people to create a crystal ball that would allow us to see what's going on in the world and even predict the future. And others are working on digital twins about Earth, about production systems, supply chains, and even people, your body and mind. I will go into this in more detail. However, the world is a complex network system, and complex network systems have a couple of features that many people are not aware of. I mean, perhaps in the back of your mind, but it really changes everything. And so what are complex systems about? As illustrated over here, in the case of many interacting people, there would be collective patterns of motion, collective behaviors, and everything depends really on small details. So the outcome can be very different. And there are many examples of complex systems, such as turbulent fluids, traffic flows, large supply chains, social, political, economic, financial, ecological systems, in fact, everything which is interesting and alive, like brain and body, the ecosystem, all of this are complex systems. And so what do we know about complex systems? Well, first of all, there are limits of predictability. We know that from weather forecasts. Weather forecasts have become quite accurate, but never exact. And it will stay like this, because we know at least some of the physics behind weather. And what we know about this basically tells us that very small changes could actually create over time very different outcomes. So even if you have 1,000,000 times more data, it will never be exact. We will not be able to predict the weather exactly in a year from now, 10 years from now, 100 years from now. Second thing is, it's challenging to manage complex systems. What you see over here are the so-called Lotka-Volterra equations. These are the simplest equations you can have in order to think about ecological systems in a mathematical way. And as you can see, there can be oscillatory cycles of the number of animals out there. And perhaps you're a hunter and you want to get the system to a certain point, say the red cross over there. And if you try to do that, it will eventually end up somewhere else. This is kind of stunning. So what are complex systems? We need to distinguish complex and complicated systems. What you see on top are complicated systems, made up of many parts, but well controllable. Otherwise, you would never buy a car. However, traffic is a complex system. When many cars interact with each other, things happen that nobody wants to happen, such as traffic jams. It doesn't seem to be difficult to drive in a circle steadily and avoiding accidents, but it turns out this is what people do. Yeah. These are not stupid people. These are people like you and me. And they want everything, just no traffic jam. Still, it happens. And why is that? Because small variations actually are amplified. So when the driver in front of you changes speed a little bit, you may respond a little bit later. And in order to compensate for that delay, basically, you brake a bit harder, and the next car even harder, and so eventually cars get stopped. This is an amplification effect. And then there's a chain reaction. So cars leave in front, but they join in the end of the jam, which makes actually the jam move backwards. So we can understand all this phenomenon, but we call this systemic instability, and it basically lets the system get out of control. There are many systems around the world of this kind. Basically, those systems for which we haven't found good solutions. Many of them are complex systems. Now, the bad news is the world is getting ever more complex because we network the world, right? So just suppose a lot of people like in this room, and we start networking with each other. I think what you exactly just did over lunch. And so this will change the dynamics of the crowd. In fact, we know that if there's enough networking, basically the properties of the components of that complex systems, in this case people, will become less and less important. And in fact, it's the network structure that takes over and determines what the outcome will be. That means the things we don't see actually are in control of what happens. And in those network systems, we may have certain kind of intentions, what you want to achieve, but often the intended effect does not occur. In many cases, there are side effects, there are feedback effects, and there are cascading effects. And we know these cascading effects, for example, from the financial crisis that everyone hoped it would be over, but actually I'm not entirely sure. So it started with Lehman Brothers bankruptcy, and then eventually hundreds of banks went bankrupt, causing losses of hundreds of billions of dollars, 100 times bigger than the initial damage. Why couldn't that be stopped? So, first conclusion, complex dynamical systems tend to self-organize. I mean, in a sense, they tend to do what they want. But establishing suitable interactions will produce desirable outcomes by itself. So, complexity is not our enemy. We just need to understand it. And we need to understand what kind of feedbacks do we need in order to make it do by itself what we want. And a good example is actually pedestrian flows. So what happens over there is that people self-organize into lanes of uniform walking directions. And this creates pretty efficient flows altogether. And this is a nice thing. It doesn't need any laws. It does not need any police. It just happens. Most people are not even aware of this. You do this every day. Did you think about it? Probably not. Job well done, in fact. Right? Now, why would you have a conference like this in a city like Lucerne, of all places? Now, first of all, it's a beautiful city, and at probably the most beautiful lake of the world. And it has a really gorgeous concert hall. I will tell you now a secret that nobody knew so far. I barely was aware of it myself. This is the place where my mother and my father met. and fell in love with each other. Now, see what happens? Here I am, right? Okay, so now something else happened actually, which is shown over here. So this is a map of the CERN, and you see this over here. So what happened there? Actually, something I personally consider quite important. Here we had a project, not myself, but my previous PhD student and the previous manager of the traffic control center in Zurich. They created a company and implemented something that my previous PhD that I was working on a couple of years ago, a traffic light control. Now, why could traffic light control be interesting after so many years? Because we did everything differently. We reinvented traffic light control from scratch, in a sense. So this is part of the intersections that they controlled. You know, if you look into the technology that is involved, it looks pretty complicated, and this is just part of the entire system, right? So just believe me, they've been working out a traffic light control, and the CERN has been evaluating it very critically, and this is the result. So waiting times were reduced for everyone, surprisingly so, even though they had a state-of-the-art system before. Minus 14% waiting times for pedestrians, minus 33 for public transportation, and everyone else minus 23. It's quite remarkable, you know, given that everything was supposed to be optimal already before. So basically, everyone had to wait less. There was more green for everyone, almost unimaginable. And why could that happen? Because we had a very different approach. And by the way, it's also good for the environment and for climate, so everyone benefits. So how does that work? Now you're expecting all the formulas, right? Yeah, so don't worry. I mean, the issue is really coordination, right? In particular, coordination of traffic flows, green waves is the key word. But the question is how to produce them. You could certainly use a traffic control center and impose green waves on the system. Those would also use supercomputers and traffic simulations and all this. Or you could do something else. This is what we did. We were inspired by what we found among pedestrians. In this case, at bottlenecks, like a door. What we found was oscillatory flows, even though nobody was actually controlling this. No police, no laws, no traffic light. But it looks like there is a traffic light, right? So we were wondering, would it be possible basically to use this principle to define oscillatory flows? That means to control traffic lights. Could we have a system where the traffic flows control the traffic lights rather than the other way around? And in fact, the idea was that we would measure the outflow from road sections, but also the inflow. And that inflow measurement would allow for a very short-term anticipation of vehicle arrivals. Just a few seconds ahead, not much more. It's not a long-term forecast. And so the question is, you know, how well would that work? So let's compare three different systems to control traffic flows. On the left is basically the system that we have today in most cities. Traffic control center, an authority that is trying to do the best job ever. Typically, technology costs many millions, and there's basically a central control based on a lot of data that's being collected in real time, and it tried to come up with the optimal control. So basically, it's a benevolent dictator approach. Now then, in the middle, we have a completely different approach, where basically every intersection decides for itself, according to the principle of Homo economicus. Strict travel time minimization. Everyone is doing the best job. but nobody cares about others. There's no coordination necessarily among neighbors. And then on the right, we do the same thing, but we are a bit other regarding because we would basically clear long queues before we get back to travel time minimization. We do that in order to avoid spillover effect, so that's why we call it other regarding. So what do we expect to be best? Well, according to common wisdom, that should be best. Centralized control, that should be second best, and this nice kind of traffic light control should be the worst. Let's see what really happens. So the top-down regulation is represented by the red line over here. So basically the queue length of vehicles increases with the capacity utilization, traffic flow, traffic volume, right? So as the traffic volume increases, basically the queue length of cars increases as expected. Now, what about the homo economicus approach? That's the violet line over here. So basically, that's much better for low traffic volumes because whenever a vehicle approaches a traffic light, it turns green, just for that vehicle. That works well for low traffic volumes, obviously, but for high traffic volumes, actually, queue lengths explode. And so the traffic control center says, yeah, see, that's why you pay us millions every year. And the question is what happens for the third approach. And that's represented by the blue line, and it turns out to be better all the way. That was quite surprising. And in fact, if we compare what happened in Lucerne before and after the new traffic light control, the bottom-up, self-organized, self-controlling system, you see this is a green wave imposed on the system. Very regular, but there's a lot of red, which means a lot of queuing, actually. This is what happens with our approach. A lot less waiting, actually, but less regular. Because basically, this system uses gaps in the traffic flow as opportunities. It responds adaptively to the actual traffic situation, rather than trying to come up with an optimal control for a typical traffic situation, which turns out to never occur. But you can't do strict real-time optimization because it's an NP-hard optimization problem. I mean, basically, computer power explodes with every additional intersection. Okay? So in conclusion, in complex systems, we cannot control everything top-down. It's not necessarily the best approach. In many cases not, surprisingly so. Now, there are also some learnings actually for production systems. So what was not mentioned is that I was actually for some time in Dresden. And we were collaborating with Infineon Technologies because they had production machines for silicium wafers, means chip production, really. But those machines were actually not working as efficiently as they hoped. So they were asking me, because they had read about our pedestrian work. But now, strangely enough, they were talking to pedestrian researchers, because their engineers actually had failed to improve the system. And so they wanted us to look at the system with different eyes from a different perspective. So we went there into their rooms, you know, we had to have all those dresses for the kind of clear room environment, you know, where every dust particle really is damaging and so on. So we looked at the system and basically does this. So you have those silicium wafers that need to undergo certain chemical treatments and in between need to be washed away with water. And all of that is being transported by one handler. So just imagine you are the boss, and the boss basically corresponds to the handler who has to coordinate all the processes in the team, right? And so the silicium wafers are the team members who want something to you or reporting to you and asking what's next. All right, so basically let's put those silicium wafers into the chemical baths, and then the next ones eventually. Now, right? And now eventually what happens is that there are two sets of silicium wafers that want to be transported, and they may want to be transported at the same time, and there's a conflict. And the handler can't do that, so someone needs to wait, and that creates delay, and if there's too much delay, actually, the quality of those silicium chips will be poor, and you can throw it all away. That's kind of the issue, right? So how do you get all of this coordinated with maximum throughput? Actually, the surprising solution was slow it all down. Because then there were less conflicts in asking for the handler. And the surprise was this really increased the throughput of several machines by more than 30%. So they were quite happy about that. So slower can sometimes be faster in complex systems. Now, what else can we say? Culture of collaboration. Let's look into democracy. And digital democracy in particular, right? So everyone now is talking about smart cities. Do you know how many smart cities we have throughout Europe? Who knows?
Like zero.
Zero. Any other feedback? Huh? -1. Come on, say be a bit more optimistic.
How do you define a smart city?
Well, I was just looking into a brochure of the European Commission, basically, you know, it was actually access restricted, even. Now, more than 200, they say. You know, and it's kind of surprising that we can't name them by name. Even less we know about what is smart about those cities, you know. What do they really do with the millions of taxpayers' money that we pay? And obviously, they buy software, you know, they do something. They don't tell us. Yeah, so yeah, everything can be made smart with sensors that are wirelessly connected to the internet, collecting all sorts of data, and then we can create feedback loops, you know, as I suggested before, automate things and so on. Clearly, this can be done. The question is, what should we do? And how should we do it? This question does not have a good answer right now, so it needs smart people like you. Okay? Now, often the question is, would a benevolent dictator be a good thing? Just like the traffic control center, you know, just collect all the data you can get hold of, put it in one place, buy some expensive piece of AI software, and then basically, you know, control it all. And it works well for production, supply chains, and but does it work well for society? Now, cities are about people, I would think. Okay? So what would a benevolent dictator do? So probably a benevolent dictator would want things to be plannable, predictable, and controllable. Okay? And in fact, there are some people who are thinking about a post-choice society even. You know, this is from a brochure that was published on a website, I think, of the German Ministry of Interior, if I remember well, about smart cities. You know, just for you to know what could come upon us, kind of a post-choice society, a post-voting society, and all this, you know, post-market society, post-ownership society, this is also even post-energy society, you know, just for those who were not alerted yet. All right. Well, this is certainly not well compatible with democracy and freedom, right? So if you care about any of those, then you should be alerted. Could be that there's a better system, though. You know, perhaps some people would want to change and want to have a benevolent dictator. If you look into the newspapers these days, you know, sometimes you could think there are some people around the world who would wish to have a benevolent dictator. But can a dictator be benevolent? Can a dictator be efficient? So, in order to do that, basically, what would a benevolent dictator have to do? So basically, try to figure out what everyone wants. Economists call this utility functions. And then determine the average of this, then find the optimal solution to this utility function, which is a goal function. So you have a goal and you want to have an optimal solution. So you use supercomputers and AI, basically figure out that optimal solution and then you implement it. You impose it on the system, like a benevolent dictator would do. Okay? Is that going to be a good thing? I'm not sure what you think about that. Everyone looks a bit scared, huh? So now, an average utility function serves many people not so well because we're not average people, right? Sometimes even quite badly. It's a little bit like this optimal traffic control that is optimal for a typical traffic situation, but the typical traffic situation never occurs, as you may remember, I said. Okay? Now, generally, goal functions are one-dimensional. So this is a grand oversimplification for a societal or social system. Societies, however, need multi-dimensional goals, have multi-dimensional goals like prosperity, sustainability, health, education, culture, and many more things. One thing is not good enough for us. Let's face it. Yeah, so when goal functions that are being used to optimize system in the world, are oversimplifying things, then the outcome cannot be good. And that's why I believe we have those polycrises. So the question is, are there any other ways to decide? And the answer is yes. Vote. And Switzerland has just done that. But the common yes-no majority voting is actually one of the worst voting methods. There are various issues. Some people are worried about the tyranny of the majority. Like the 51% could basically determine what everyone, 100% of people have to do. So basically, hand over control to a few people for 4 years, and they could be like a dictator. Almost. Not in every country, but this is one concern. And this concern certainly is becoming increasingly real in some countries around the world. Another point is actually that the majority rule undermines spatial fairness. So let's talk about cities. Cities have districts, and districts have different numbers of people. So if you have majority voting, then basically those districts that have the most people will basically always win. And what you then get is that basically most of the money goes to the center, because those are the most populated areas typically, and there would be social issues in the periphery. Like we know that, for example, from France, but also other countries, the banlieues. Over many decades, this is not going to be good for society. So we need different, better voting rules, okay? So then let's remember what is voting about. So where can we change something? The first thing is we need to know about voter preferences. What do you want? And that can be measured in different ways, in simple and complicated ways. That is done basically by a ballot, where you make your cross or whatever, and then that goes into the ballot box, and then follows a vote aggregation procedure that determines the outcome of the vote. Now, what can be varied here? Basically, in order to look into this, we have created an app. It's called Vote App, and in this Vote App, we have varied different procedures. One thing that can be varied is actually the voting input. right? So how can you express your preferences? And in many cases, it's just approval voting. So you have some options. You can say, I want this or that. There are other ways also to measure what you want. Combined approval voting, for example. Here you can either approve, this is 1, disapprove, which is -1, or abstain, which is represented by 0, okay? So it's more detailed. It tells more about your preferences, okay? Another approach is rank voting, the so-called border score, and here basically you're ranking those different options according to your preferences. And finally, it's not actually the last possibility that we have, but the last one which I mentioned today is cumulative voting, where basically you have 10 points, say, that you can distribute as you like over different options. So you can express how much you like a certain option, okay? Now what happens in the ballot box? So basically now it's about the aggregation, okay? And here we can also vary a number of things. So majority voting just counts the number of votes, and basically those projects that get most votes, or the candidates, they will be it. Okay, but what this approach basically neglects is the cost. So if we talk not about candidates, but if we talk about different projects that we could implement in the city, a new city hall, a new park, some trees, you know, a kindergarten, whatever, then there are costs attached. And so perhaps it's not a bad idea to take those costs into consideration. And so this is important for what is called participatory budgeting. And here we could basically also look at how many votes as compared to the cost does a certain project get. And then basically give those, basically implement those projects that get most votes per cost unit, okay? And then there's another approach which is called equal share, where basically virtually you're being given a certain sum of money and you can distribute that over those different projects, you know, and those projects that get enough money to be implemented, basically they will be it. Now why is this interesting? Because actually the voting rules can change the outcome. While the classical majority voting approach basically gives money just to a few projects, and typically to the most expensive ones, and there's no money left for everyone else, you know. You see on the middle and on the right that the other voting rules can actually have different outcomes, where there are many more projects that can be supported. So projects are more diverse, and it's more inclusive, right? And now, so far it was just theoretical. But you know, sometimes the revolution happens in places where you don't expect it to happen. And it happened in Barcelona, but it also happened in Aarau, Switzerland, just close by, where nobody perhaps would have expected that a project will happen that would change everything. Because what we're talking about is trying to find a system that is better than optimal. Better than optimization. All right, so Aarau really did the experiment. We had a field study. We were involved. So they did a participatory budgeting exercise. So basically they took a certain amount of money, put it aside, and said, okay, now citizens, you can make proposals what we should do with this money. Okay, and there were basically meetings, hoping basically to unleash the collective intelligence of the people. So there were citizen workshops, deliberating, coming up with ideas, discussing about benefits of those approaches, brainstorming. I see the city of Aarau over there, and also already some sticky notes that basically have some ideas on it related to different quarters of town. So this was made more and more concrete over many sessions, and so basically in the end there were a number of projects that were concrete enough and feasible for implementation that they came onto the list that people could select from. So not only could people vote for those projects, they could also come up with those projects. So everything was bottom up in a sense. But city council of course had people involved in each step of this, so there was trust on both sides. Trust was created by transparency, and of course people were told how the voting would work, because we had those special voting rules, and this was explained on a web page. I think it's still up, you can find it, kind of Stadtidee Aarau. And then finally there was the final countdown. Okay. And this determined 17 projects, all right? So all the ones with the red dot, basically, they happen to have a good ratio between votes and costs. But the good thing was, it was a lot more projects that could be supported than what the majority rule would have come up with. Majority rule supported 7 projects, and the way we did it supported 17 projects. Those 17 projects were distributed all over the city, so I think all city districts actually got a project, while the majority voting just put all the money into one basket, basically into the center. And what we also cared about is voter satisfaction, of course, right? So that also went up. So there are a lot of benefits just by changing the voting rules a bit. So democracy can be upgraded. And I do think companies could also use similar approaches actually to decide how to invest money. Question is, how can the economy be upgraded too? And it was just arriving with public transportation. The bus ended at a stop that was called Allmännlich. So I hope you know what this means. Allmende is something which is like a common good. And actually, Elinor Ostrom, Nobel Prize winner in economics, got the Nobel Prize for studying common goods, and she did that in Switzerland, by the way. So, can we learn something from a Nobel Prize winner? Well, we have been raised basically with the thinking of the survival of the fittest. And that's also perhaps the common paradigm in economics, right? But are people really so selfish as it's often claimed? And in fact, a couple of years back, people did experiments and with very surprising results, actually. So one of these experiments was I would give somebody some money and would ask the person to decide how much money to give to somebody else. Could be nothing, could be everything, could be part of it. So selfish people would give nothing, right? That's the dictator game, by the way. It turns out that in many countries, most people give between 20 and 40%. So people are not as selfish as we think. There is also an ultimatum game where basically I give money to somebody, and then that somebody decides how much money to give to somebody else. And that other person could basically turn down the offer, then nobody gets anything. And otherwise, everyone just gets how much was offered, and the first person gets the rest. Okay, it turns out that in this case, people tend to give around 40%. So they don't give nothing typically. There are some people who do that, but typically people are, again, less selfish than expected. And this was shocking to economists, So it was in clear violation with the economic paradigm at that time. And so I decided that we should basically do a computer simulation about selfishness of people, right? And so we call this so-called agent-based simulation. So people are represented by simplified people in a computer called agents. They mimic people, and they interact with each other according to rules that we can decide. We can also give those people in the computer a memory. We could give them the ability to learn, to change their behavior and all this, to change their preferences. We did that in a very simplified way in this paper over here. And so we were basically trying to simulate human evolution in a computer. So these are the 4 rules. Basically, people decide according to a best response rule, which basically means they strictly maximize their utility. They do just what is best for them. Okay? Economic thinking. However, this utility function can consider actually the payoff that interaction partners of us would get. So we could be friendly by considering other people's payoff. And this friendliness is assumed to be inherited to offspring, I mean to children basically. But the likelihood to have an offspring increases exclusively with the own payoff, not utility. So the money you really have and can spend on your children and anything else. And friendliness tends to be that of the parents, so this is inheritance, say genetic inheritance or inheritance through culture and education, whatever. But there's also some mutation rate. So basically that's the assumptions that we have in evolutionary biology. So what would happen? We start our simulation with totally selfish people. Everyone just tries to maximize their own payoff. Nobody cares about others. There's no friendliness. But surprisingly, after a couple of dozen generations, everything changes. So there is an outbreak of friendliness. Cooperation goes up. In the beginning, cooperation is a bad thing because basically you're being exploited for being cooperative. But in the end, cooperation thrives, and those who are not cooperating, the so-called defectors, are actually doing a bad job. So really, the system changes completely from totally selfish to somewhat friendly. In fact, about 40% friendly, on average. But there is some variation, that not everyone is the same, we know that. And in fact, I can show you some experimental results. So there are selfish people called individualistic here. These are experimental results, as I said. But most people have some pro-social tendency, okay? By the way, even Adam Smith knew that back in 1759. I mean, it's where he said, I've gendered that a bit. However selfish humans may be supposed, there are evidently some principles in their nature which interest them in the fortune of others and render the happiness necessary to them, though they derive nothing from it. So, surprisingly, evolution has made many of us other-regarded to some extent. And it basically means we need a new kind of economic thinking. We are not well represented by this concept of Homo economicus. We need a new economics, and we need a new economy, basically. And the question is, will the survival of the fittest be eventually replaced by the survival of the nicest? Now, what I have been talking about is something that we can call the evolution of networked thinking or networked minds. So when people act friendly, they start caring about others. They think about others' outcomes when we interact with each other. That's what the Homo economicus doesn't do, but Homo socialis does. And as I said, this feature that we start thinking about others allows us actually to be cooperative and to thrive all together. That means have a better societal outcome and everyone else of us too. Now things get interesting again. So the question is, should we have networked minds or networked brains? Now I really talk about high-end technology, all right? Perhaps you've never heard about it. So there's a document, a manifesto back in 2016 about the future of healthcare, and it talks about an internet of humans. Were you aware of that? So there's a new frontier, the convergence of nanotechnology, brain-machine interfaces, and artificial intelligence. In fact, you know, the World Economic Forum has informed us back in 2020 that tracking how our bodies work could change our lives. You know, everyone would agree, I guess, right? But what you perhaps don't know, this could be based on nanotechnology. That means very small, minute particles that are so small you can't even see them with your eyes. You need a microscope for that, or even an electronic microscope. And you basically can put those particles into people's bodies and use it to read data out of the body. You know, it's kind of the Internet of Things transferred to bodies. And then in the same year, the World Economic Forum told us the Internet of Bodies is here. All right, how does that work? I mean, you've heard about brain machine interfaces, right? And you probably think of Elon Musk and Neuralink now, and you think, oh, he's working on brain chips, and one day these brain chips could be put into people's brains. And perhaps you like this idea. Who would want to have such a brain chip? And let's ask over here. That's 50% off today. So who orders that brain chip? Nobody. So, you know, perhaps you would say, I don't want such a thing. I will never go to the doctor to have it implanted, so it's not my problem. But what if we would not need a brain chip for such neurotechnology to work? What if we could build it in a different way? This brings us to the Internet of Nanothings, or bio-nanothings, actually, right? Where all those nanoparticles that I was talking about, those minute particles would be spread around our body cells and be used, basically be read out with certain devices, could be even our mobile devices, as you can see over here. And so that would be something like in-body surveillance. Would read out a lot of data. It would be useful for personalized medicine, for high-precision medicine. You could do fantastic things with it. But you could also know what is happening in your body. Okay? Back in 2013, the BRAIN initiative was launched. This one actually wanted to deepen the understanding of the inner workings of the human mind and to improve how we treat, prevent, and cure disorders of the brain. Okay? So, out of this comes a brain activity mapping project. And this is about, I just read this one sentence. Nanoscience and nanotechnology are poised to provide a rich toolkit of novel methods to explore brain function by enabling simultaneous measurement and manipulation of activity of thousands or even millions of neurons, your brain cells potentially, you know, in the future. We and others refer to this goal as the Brain Activity Mapping Project, and this is why it is expected, according to a big tech company, that the amount of data that we produce would not double anymore in 12 months' time, but eventually every 12 hours. Okay? And so that would require something like a human brain cloud interface. There are people thinking about it. Some of it is theoretical, but there are people who really try to make it happen. Now that could really change our society and our economic system. In this case, they even talk about pico-economics, but basically neurocapitalism could be implemented. I would be kind of the successor of surveillance capitalism. You know, in surveillance capitalism, which we have now, it's possible for some companies or secret service to know basically everything about you. And, you know, that's a fact of life now. Here, they could also manipulate the way you think and feel and what you do. So that's neurocapitalism, right? So it could be a fantastic thing. Who likes it? No? So perhaps we need some international regulation. So with this, I'm actually at the end of my presentation. I think I've highlighted the potentials of AI and digital technology, and that there are huge opportunities, but also quite some risks. And these are my take-home messages, among others. So complex systems behave often differently from what we think. Self-organization is a typical phenomenon and can be, however, a superior form of organization. So complexity is not our enemy. We just need to learn to understand it and how to use it for us. Slower processes can sometimes be faster and improve the system performance. Networked thinking can promote cooperation and benefits for society. Then the question is the internet of bodies or the internet of humans coming? Who thinks it's coming? Yes, 3, 4, 5, come on. There are quite a few people who think it could be coming, okay? And then the question results, should we do everything technologically feasible? Thank you very much.